Everybody, now that you understand how different number systems work, I want to make sure that you can switch between a number represented in one base to a different base. Now, we already did a little bit of that in the last lesson, so that's where we're going to start out. Okay, so in our last lesson, we saw how to write numbers in expanded form. Let's write the number 8f.b05 base 16 in expanded form, and then convert that into the decimal equivalent. Okay, we'll do this one together. Okay, so we already know how to do this. We're working in base 16. It's important to recognize what each placeholder represents. So our f is in the ones place. That's our 16 to the zeros place. And the next spot over would be the 16 to the first or the 16s place. This is 16 to the negative 1 place. We'd have 0, 16 to the negative 2's, and 5, 16 to the negative 3's, and so on. So let's go ahead and expand that. When we do, we have 8 times 16 to the first, f times 16 to the 0, b times 16 to the negative 1. There are no 16 in the negative 2 terms, and 5 times 16 to the negative 3. Now, let's sort of decode that. 8 times 16 to the 1, that's 8 times 16. F, as you should remember, is equal to 15 times 16 to the 0, but that's just a 1. B, hopefully you remember, is 11 times 16 to the negative 1, which is 1/16. And 5 times 16 to the negative third, that's 1 over 16 to the third power, which is 4096. Okay, so all we need to do is compute that, and we'll have our decimal equivalent. 8 times 16 plus 15 times 1 turns out to be 143. There's our integer part of the number. And 11 times 1/16 is 11/16. 5 times 1 over 4096 is 4096. This is definitely calculator work, and that turns out to be 0.6887 rounded off to 4 decimal places, and we've converted that over to base 10. So we already know how to convert from any number base over to decimal. We do that by expanding. Okay, so I'd like you to do this one. Take the number 604.72 base 8 and write that in decimal form. Work that out and unpause the video to see that solution. All right, I always like to identify that first ones place, and in this case, since we're talking about octal, that is 8 to the 0, and then I'm less likely to make mistakes when I expand that. So 8 to the 0, 8 to the 1, we have 6 8 to the second power, no 8 to the first power, 4 8 to the 0th power, 7 8 to the negative 1 power, and 2 times 8 to the negative 2 power. Okay, so there's our expansion. We can figure out what those values are worth. So we have 6 times 64, that's 384. We have 4 times 1, which is 4. We have 7 times 1/8, which is 7/8. And we have 2 times 1/64, that's 2/64, which of course you could reduce, but we don't really need to. And so our number in base 10 will be 384 plus 4, that's 388.90625 when we convert those fractions into a decimal. And that is now base 10, and you've performed the conversion. The key here is anytime you want to convert from a number base into decimal, we do it by expanding in this way. So you already know how to convert any number to decimal. What we want to focus on in this lesson is going the other direction, taking decimal numbers and converting them into an alternative number base. Okay, so let's start with an example. Let's convert 85 as a decimal number, base 10, into binary. There are a lot of different techniques for doing this. If you find an alternative method that you like, go ahead and use it, but this is the method I prefer. The first thing we do is we create a binary conversion table of sorts by writing all the powers of 2 from right to left. So if we write all the powers of 2, we'd start out with 2 to the 0, which is 1. 2 to the first power, which is 2, and so on. 4, 8, 2 to the fourth is 16, 2 to the fifth is 32, 2 to the sixth is 64, 2 to the seventh is 128. And once we've gone past the number that we're converting, we can stop. Now, because our last digit here is a 1, that's our 1's place, this is our 2's place, our 4's place, and so on. This is where the binary point will go in our number. Now, here's what we need to do. Step 2, we just find the highest power of 2, the number on this list, the biggest one that's no bigger than 85. Well, the biggest one that's no bigger than 85, 128 is too big, right? So we're not going to use that. 64, and that's where our first 1 goes. So 64 goes into 85 just one time. And then we need to figure out how many are left. So we take 85 minus the 64 that we just allocated, and we're left with 21. Now we start that process again. We say, all right, well, what's our highest power of 2 on our list that fits into 21? Well, 32 doesn't fit into 21, so we're not going to use that, and we can put a 0. But 16 fits into 21, so let's put a 1 right there. And so then we're going to take our 21 and subtract off the 16 that we just spent, and that leaves us with 5. All right, and we start the process over. What's the biggest power left on our list that doesn't exceed 5? Well, it's not 8, that's too big. It's 4, so we're going to spend a 4, and we're going to take that off. And that leaves us with a 1. So we have no 2's and we have a 1. And so there's our binary representation. It is 1, 0, 1, 0, 1, 0, 1, base 2. Now to convert that back, you can kind of see we've already done it. That means we have one factor of 1. We have no factors of 2. We have a factor of 4. We have no factors of 8. We have one factor of 16, no 32's, and a factor of 64. And if you take 64 plus 16 plus 4 plus 1, you get 85. And we're done. Okay, you might want to rewatch that process if necessary, but I'm going to give you one for practice here. Take a minute, and I would like you to convert the number 157 base 10 into binary. Go ahead and pause the video, do that, and then unpause to see if your answer is right. Okay, well, here we go. And again, we're going to make our conversion table, which basically just means we're going to list all the powers of 2 from right to left. So here we go. 1, 2, 4, 8, 16, 32, 64, 128, and this time we're going to have to go one higher. That's 256, and now we've exceeded 157, so we can stop. All right, here we go. We're not going to need that 256. The highest power of 2 that fits into 157 is 128. That's going to be our first non-zero digit. So let's take 157, the number that we're trying to convert. We just spent 128 of those, and that leaves us with 29. So 64, nope, that's too big. 32, that's also too big. 16, that's the next power that fits into 29, so we can spend 16. And that leaves us with 13. Another way to think about this is think of them as being points you have to spend or dollars that you have to spend. We start out with $157. We can't buy something worth $256, but we can buy something for $128, and we'll have $29 left over. Once we have $29 left over, we say, can we afford something for $64? Nope. Can we buy something for $32? Nope. Can we buy something for $16? Well, yeah, we can. And if we do, we'll have $13 left over after we make that purchase. Now, can we buy something for $8? Yes, we can. So we're going to spend 8 of those, and that's going to leave us with $5 left over. Can we buy something for $4? Yep. And if we do that, we'll have $1 left over. So we can't afford anything for $2, but we can afford something for $1. And there's our binary representation. 1, 0, 0, 1, 1, 1, 0, 1, base 2, and that is equal to 157 base 10. And we're done. You've performed the conversion. Okay, let's steal that idea now and work with other number bases. Let's write the number 647 base 10 in hexadecimal. We really use the same process, it just looks a little bit different. Well, so let's create a hexadecimal conversion table of sorts by writing all the powers of 16 from right to left. So of course 16 to the 0th power, that's going to be 1. 16 to the first power, that's our 16's place. 16 squared is our 256 place. And 16 to the third power is 4096. Okay, so we created our conversion table that we're going to use here. Let's determine the highest power of 16 that is no bigger than 647. Well, 4096 is definitely way too big, so we're not going to use that spot. We are going to use 256. Step 3 says determine how many times that power goes into our number, 647, and figure out the remainder. A good way to do this is to use good old long division. So we're going to take 647 and divide it by 256. Well, 256 fits into 647 2 times. You could use your calculator to help you if you needed to. That means that our first digit in our hex number is going to be a 2. Okay, now we got to figure out what the remainder is though. 2 times 256, that's 512. And we subtract that to be left with 135. It's like saying we have $647 to spend. We can buy 2 items for $256, and that means we'll have 135 left over. Now we're going to repeat that process for the next spot over. We have 135. Does 16 fit into 135? Well, sure it does. So let's set up that division again. 135, this time we're going to divide that by 16. And 16 fits into 135. Well, if you don't know, use your calculator. 135 divided by 16, 8. We don't care about the decimal. All that matters is that 8. So that's going to be 8, and that tells us that our next digit in our hex number is 8. Now multiply that around. 8 times 16 is 128. We subtract, we're left with 7. And how many times does 1 fit into 7? We could write out the division if we wanted to, but 7 divided by 1 is, of course, 7. And so that's our third digit. And we're done. So we can conclude that 647 base 10 is the same as 287 base 16. And we've performed the conversion into hex. Okay, well, it's your turn to give that a try. Watch that again if you need to, but I would like you to pause the video and convert 999 base 10 into hex. Unpause when you want to see that solution. Okay, so here we go. Step 1, let's make our conversion table. List the powers of 16 since we're going to hex from right to left. 16 to the 0th power, that's 1. 16 to the first power, that's 16. 16 squared, that's 256, and 16 to the third is 4096. That's plenty. Okay, step 2, find the highest power that fits into 999. Well, 4096 is again too big. 256 is the biggest power. So we need to see how many times it fits in there and get our remainder. So let's take 999 divided by 256. 256 fits into 999 3 point something times. All we care about is that 3. And that tells us that our first digit in our conversion will be a 3. Now what's our remainder? 3 times 256, you can check that on your calculator if you want, is 768. If we subtract that, we get 231. And now we start that process over again. Now we're going to see how many times 16 fits into 231. So 231 divided by 16, 14 times. Now remember, we're in hexadecimal, so this is important. We don't want to call that 14 a 14. There's a name for the number 14 in hexadecimal. Do you remember what it is? Yeah, it's E. And so we're going to call that 14, not a 14, but an E when we write that in hex. Now, what's our remainder? 14 times 16, that's 224. and when we subtract, we get 7. And so again, our last digit turns out to be a 7. So there you have it. 999 base 10 is equivalent to 3E7 when converted to hexadecimal. Okay, let's just do one example of decimal to octal. Let's convert 723 base 10 into octal. Okay, let's make our conversion table. So 8 to the 0th power, of course, that's a 1. That should always be a 1. 8 to the 1st power, that's 8. 8 squared, that's our 64's place. 8 to the 3rd, that's 512. 8 to the 4th power, and that is 4096. Okay, so what's the highest power that fits into 723? Well, 4096 is too big, it's 512, and so we're going to set up our division. How many times does 512 go into 723? Well, that one's pretty easy. It's going to fit in there one time, and that tells us our first digit will be a 1. Now let's figure out our remainder. 1 times 512 is 512, and we subtract, we get 211. That rolls into our next step. So 211, we're going to see how many times 64 goes into that. 64 goes into 211 3 times, and so our next digit's a 3. What's our remainder? 3 times 64, that's 192, and if we subtract, we get 19. That leads into our next step. Let's take 19 and divide it by 8. 8 fits into 19 2 times. There's our next digit. 2 times 8 is 16, and if we subtract, we're left with 3. And we don't really need to show it, but then if we take 3 and divide it by 1, we get 3, and that is our last digit. So apparently 723 with a base of 10 is the same as 1323 in a base of 8, and we're done. Okay, so now we know how to convert numbers from decimal into any other number base. But what if there's, those were all integers. What if there's a part of a number like 0.58? Let's take the number 9.58 and convert that into binary. So step one, we're just going to convert the integer part of our number, that is to say our 9, into binary. That's what we just finished doing. So let's start with the 9. List all your powers of 2 starting at the right, and so we have 1, 2, 4, 8, 16, and that's going to be enough for our purposes. What's the biggest one that fits into 9? Well, 16 doesn't, but the 8 does, and so 8 fits into 9 one time. And of course 9 minus 8 is going to leave us with 1 left over, so it's going to be no 4s, no 2s, and that 1 left over. So 9 is equivalent to 1001. That's the first part of this process. So at this point we know 9.58 is going to be 1001, that's the 9, and that's where our binary point will go. Now the question is really, how do we convert the 0.58 to binary? That's actually pretty easy. Here's what we're going to do. We're going to take that decimal part in step 2. We're going to multiply that decimal by our new base. So since we're going to binary, we're going to use base 2. We're going to take 0.58 and multiply it by 2. And if you do that on your calculator, you will get 1.16. Notice the 1 there. That 1 becomes the first digit to the right of our binary point. So that 1 gets recorded, and then we throw it away and we repeat the process. Let's take the decimal off of that, 0.16, and multiply it by 2. 0.16 times 2 is 0.32. Look at that, we got a 0. So we recorded that, we take the decimal point and we repeat. 0.32 times 2, that's 0.64. That generated another 0. And now we're going to take the 0.64 times 2, and we get 1.28. So there's a 1 this time, so we're going to keep that. But here again, now we lose it when we multiply, so we're just going to take 0.28 times 2, and we get 0.56. That's another 0. And we could continue this as long as we want. But we can quit there. We usually go about 5 places to the right of the decimal. If it doesn't end by then, we just quit. And 9.58 base 10 is 1001.10010 base 2. So I would like you to try that process. Convert 15.043 base 10 to binary. Work that out and unpause to see if you get the right value. Okay, so let's start by converting the 15. List all your powers of 2, since we're going to binary, starting from the right. 16 is too big, it doesn't fit in there, but 8 does. 15 minus those 8 leaves us with 7. The highest power that fits into 7 is a 4, so we'll put 1 there. That leaves us with a 3. 2 fits into 3, so we'll have a 1 there. And a remainder of 1. So 15 is equal to 1111 in binary. So at that point, we know what the first part of our number is going to look like. 15.043 base 10 is the same as 1111 point something base 2. Now let's figure out what our places to the right of the binary point are going to be. So again, we take that decimal, 0.043, and we multiply it by 2. And that gives us 0.086. That gave us a 0 as our leading digit, so we record a 0. 0.086 times 2 gives us 0.172. Again, another 0. 0.172 times 2 is 0.344. Another 0. Now you could certainly do this on your calculator more quickly. I just want to make sure you understand the process. But if we take 0.043 times 2, that gave us a 0. Times 2, there's our next 0. Times 2, there's our next 0. Times 2 again, 0.688, that's another 0. Times 2, there we got a 1. Now we can subtract that off and multiply it by 2 again. And we have a 0. Times 2 again, there we hit a 1. Subtract it off, times 2, and we hit another 1. And so you can see that you can crank out these places really, really fast. 15.043 base 10 is 111.00001011 base 2, and that continues on, but we will stop right there. Okay, well, this exact same process works to convert a fractional or a decimal part of any number into any other number system. So let's write the number 14.823 in hex. Okay, step 1, convert the integer part of the number. Now notice that we're starting out with 14 and we're going to hexadecimal. 14 has a name, doesn't it? 14 is E, so we really don't have to do anything there. 14 is E. So this is going to be E point something in hex. So we're going to do the same thing we did with binary. We're going to take our decimal part of the number, 0.823, and we're going to multiply it, not by 2. We're going to hex here, so we're going to multiply this by 16. So if you do that on your calculator, 0.823 times 16, and we're left with a 13. Now, that 13 is our next digit, but of course we're in hex, so we don't want to call 13 13. 13 is represented by D. So our first digit to the right of our hex point is 13. Now we'll subtract that off, and we get 0.168, 0.168. I'm writing this down, but you certainly wouldn't have to. Now we're going to multiply that by 16 times 16, and we get a 2.688. 2 is our next digit. We're going to subtract that off, and we have 0.688. We're going to multiply that by 16 times 16, 11.008. Well, we know what 11 is, right? That's B. Minus the 11. And that leaves us with 0.008. Let's multiply that by 16. and we get 0.128. There's a 0 there, so we have to record that. Now let's multiply that by 16 again, and we get 2.048, so we have another 2. And again, we could continue with this as long as we want to go in. 5 hex places is probably enough. We'll stop there. We'll talk about that a little bit more in a later lesson. And so 14.823 base 10 is E.D2B02 base 16, and we're done. That happens pretty fast. It's actually a really quick process to convert a decimal part of a number into another base. You just repeatedly multiply by that new base and peel off the integers that come off on your result. If you want to watch that again, by all means do that till you feel like you've got it, and then go ahead and do this one. Convert 1634.451 base 10 into hexadecimal. Okay, here we go. Let's start with the integer part of this number, 1634. We're going to hex, so let's make our conversion table. This one's a little bit more work than the previous one. 16 to the 0th power is 1. 16 to the 1st power is 16. 16 squared is 256. And 16 to the 3rd is 4096. If you don't have those memorized, you will soon. The biggest power that fits into 1634 is 256, so we're not going to need that. So let's take 1634, and we're going to divide that by 256. We're finding out how many times 256 goes into that number so that we figure out our first digit. 1634 divided by 256, turns out that it fits in there 6 times. So there's our first digit. We have a 6. Now 6 times 256, I don't really need to show that. That's 1536. Subtract, and we're left with 98. So we move over. How many times does 16 go into 98? Well, we just repeat the process again. 16 goes into 98 6 times. That tells us our next digit. 6 times 16 is 96. Subtract, and that leaves us with 2, and that'll be our last digit. So 1634 becomes 662. So I'm going to scoot that down here. We know that this is going to be 662 point something. The question is point what? So now we're going to take the decimal part of that number, 0.451, and we're going to start multiplying that by 16. We get 7.216, so that tells us our next digit is a 7. But we record the 7 and we just keep the decimal part, 0.216 times 16. That gives us 3.456. We'll keep the 3, subtract it off, and we'll take 0.456 times 16. Fell behind on my process there. And we got a 7. Subtract off that 7 after we record it. Take our decimal times 16. 4.736. There we'll keep the 4. Subtract it off. Multiply by 16. And we get 11. That's a hex digit. That's B. And we could do this all day long. Minus that 11 times 16. 12. So we have C. And we could go as many places as we want. Yikes, I went 6 there. We don't really need that many, but we'll quit right there. And we've converted that over. Okay, well, we're done with the heart of this lesson. I just want to stop here and summarize to make sure that you see the 2 main pieces of information that we've seen so far. First of all, if you want to convert either binary or octal or hexadecimal over to base 10, that is to say to decimal, just write that number in expanded form as you saw in the last lesson, and then add the terms together. That's the first thing we did in this lesson, and pretty much what we focused on in the last one where you became familiar with number systems. So it's not hard to go from binary, octal, or hexadecimal over to decimal, and you can handle that. What this lesson focused on was the other direction. If you want to convert decimal into binary, octal, or hex, then we use that kind of makeshift conversion table where we list all the powers of our base starting from the right and working to the left, always starting with 1. And then you use repeated division in that 4-step process. I won't give that here, but in earlier examples in this lesson, that 4-step process through repeated division will tell you what your new digits will be in your new number. And of course, if there's any decimal places on that decimal number, that is to say to the right of the decimal, you can take that decimal part of your number and multiply it by the new base. That's either 2, 8, or 16 repeatedly. Each time you grab that front digit and peel it off, and those tell you your new digits to the right of your octal, hexadecimal, or binary point. Okay. Now there's one more kind of clever type of conversion that I want you to be aware of. We'll do a couple examples of that and then we're going to wrap this up. Okay, well then you're probably thinking, well, what if we're not trying to go into or out of decimal, but just trying to go between binary and octal or binary and hex? Well, as it turns out, that's the easiest conversion of all to do, and let's take a look at why. First of all, I need you to recognize one important thing here. Let's talk about octal for a minute. I think you would agree that 0 base 8 is the same as 0, 0, 0 base 2. So in other words, 0 in a base of 8 and 0 in a base of 2 are the same thing. That's easy enough, but let's take that a step further. 1, 1, 1 base 2, what's that equal to? What's a binary digit 1, 1, 1? Well, that's 1 plus 2 plus 4. That's equal to 7 base 8. So here's what I want you to see. 3 digits of binary is enough to represent 1 digit of octal, and that is always true. The biggest octal digit is 7, and 111 is the biggest number we can put in 3 binary digits. Everything between 0 and 7 could be represented by something between 000 and 111 in binary, and we don't need to list everything in between. The same thing is true for hex, but we need one more place to do it. 0 in base 16 is equal to 0000 in binary. But what do we have if we have 1, 2, 3, 4 ones in binary? 1, 1, 1, 1? Well, that's 1 plus 2 plus 4, that's 7 like we had back here, plus 8, another spot, that makes 15. And 15 in hex is F. So it's the same idea. The largest value we can have with 1 digit in hex is F, and the largest value we can have in 4 digits of binary is 111. That means this. To convert binary to octal or hex, we just group the digits either in groups of 3 if we're going to octal, or groups of 4 if we're going to hex. And we always start at the decimal point and work out in each direction. Let's see what that looks like. So we're going to convert this binary number, I'm not even going to say that, to hex. Let's drop the decimal straight down. Now the first 4 places to the left of the decimal are 0001. So what does 0001 in binary become? Well, that's easy. That's still a 1 even in hex. Now I'm going to switch to red. Not that it's wrong, I just want you to see these numbers pop out a little bit. The next group of 4 digits are 1111, and we just saw a minute ago that 1111, if we're converting to hex, that's F. The next 4 digits over are 1100. 1100, well, that's no 1s, no 2s, 1 4, and 1 8. That's 12. But 12, when we convert that over to hex, is C. Now when we get to the end, there aren't 4 digits. There's only 2. But we can always make it 4 by putting a couple zeros on the end. And so our last group is 0010. And what's that equal to in hex? Well, that's 0 1s, a 2, no 4s, and no 8s. So that's just 2. And so the integer part turns out to be 2CF1 when we convert it to hex. Now let's do the same thing, but let's work to the right of the decimal. 1100, we saw that back here. 1100, that's 12, which is C. The next 4 over are 1001. That's a 1, no 2s, no 4s, and an 8. So that's 9. And then we again run into a stray 1 hanging off the end, but we can make it a group of 4 by putting 3 zeros after it. And so we end up with 1, 0, 0, 0. That's no 1s, no 2s, no 4s, and an 8. And there it is. We've converted this thing to hexadecimal. Okay, let's do that one more time, but this time let's use all the same principles and let's go to octal. So we're going to do the exact same process, but the difference is we're going to group by groups of 3 this time. So here again, I'm going to drop that point straight down, and let's go in groups of 3. Our first 3 digits are 0, 0, 1. That is, of course, equal to 1. Our next 3 digits are 1, 1, 0. That's 0 1s, a 2, and a 4. That's 6. Our next 3 digits are 0, 1, 1. That's a 1, a 2, and no 4s, so that's 3. The next 3 digits are 1, 1, 0. We saw that earlier. That's another 6. And our next 3, we need a 0 to complete the group of 3. We just have a 1 in the 2 slot. And so it's 2, 6, 3, 6, 1, point. Let's work our way to the right. The first group is 1, 1, 0. We've seen that before. That's 6. Our next group is 0, 1, 0. That's 2. And our last grouping is 0, 1, 1. That's 3. And so there is our number. When we convert that to octal, this becomes 26361.623 base 8. And we've converted it over. Okay, it's your turn. Give this one a try. Take that number, write it down carefully, and I would like you to convert that number to hexadecimal. Okay, let's take a look. 101011.0111011. Okay, we're going to hex, so you should group these by groups of 4. Again, I'm going to use red for a contrast, but this is not an error that I'm trying to warn you about. Bring our decimal straight down. 4 groups to the left, that's 1011. 1, 2, 4, 8. So 1 and 2 and 8 makes 11, but 11 is B. The next group of 4, 1011. Oh, that's the same thing we just had, right? So that's going to be another B. And to the left of that, we need a couple zeros to make a group of 4, which means no 1s and a 2, 2. So 2BB, point, let's work our way to the right. 0, 1, 1, 1, 1, 2, and 4, but no 8s, that's 7. And the next group, we need a 0 to make a group of 4, and we have 0, 2, and 4, that is 6. And so it is 2BB.76 base 16, and we're done. Okay, well, going the other direction uses the exact same principle. So here we go. Let's convert each of these into groups of 4. Let's start by working our way to the left. A is equal to 10 in decimal notation, and 10 is going to consist of an 8, no 4s, a 2, and no 1s. So 1010. 3, that's 3 of course, and so that's going to be 0, 0, and a 2, and a 1, 0, 0, 1, 1 when we convert to binary. 7, well, that's of course 7, and so we're going to have 0, 1, 1, 1. 4, 2, and 1 makes 7. So we've converted the left half to binary. Let's convert the right half. 0, we like that. 0, 0, 0, 0. Again, we're using groups of 4 because we're going to hex. Our next digit is a 9. So what does 9 become when it goes to binary? That's going to be an 8, a 0, a 0, and a 1. So 1001 when we go to binary. An 8, no 4s, no 2s, and a 1. And finally, C. Remember, C represents the number 12, and we make 12 with an 8 and a 4, no 2s, and no 1s. And there it is. We've converted that to binary, and we're done. One more. Let's convert one octal number back into binary, 731.05. Well, let's bring our point straight down and work our way to the left. Again, we're going to 8 now, and so we should be using groups of 3. We only need 3 binary digits for every one of these octal digits. So we'll start with 1. That's 0, 0, 1. There's our first group of 3. Our next digit is 3. That's 0, 1, 1. Our next digit is 7. That's 1, 1, 1. Moving to the right, we have 0. Again, we like those. Followed by a 5. And a 5 in octal is a 4, no 2's, and a 1. So 1, 0, 1. And there it is. We've converted that to binary. So there it is. There's the last problem of the lesson. I would like you to take 3C6.F04 in hex and convert that into binary. Pause the video, group those up, and unpause to see if you get all these 1's and 0's right. All right, let's take a look. 6 in binary. That's no 1's, a 2, and a 4, and no 8's. So again, we're grouping by groups of 4. 6 becomes 0, 1, 1, 0. C. We know that C is 12, and we've done that one before. That's going to be an 8, a 4, no 1's, no 2's, and no 1's. And 3 is, of course, 0, 0, 1, 1. So we've got the left half of our number. Let's take a look at the right half. F. F is equal to 15. That's the highest hex digit, and so it's going to be the highest number we can make with a group of 4, or in other words, 1, 1, 1, 1. That's 8 plus 4 plus 2 plus 1. One that's even easier is 0, 0, 0, 0, 0. And we're going to finish that off with a 4, which is no 8's, a 4, no 2's, and no 1's. And so there's our binary equivalent. So you should have, we don't need these 1's out in the front for our binary representation. So 1, 1, 1, 1, 0, 0, 0, 1, 1, 0, point. 1, 1, 1, 1, 0, 0, 0, 0, 0, 1, and we don't need those zeros on the end either. And you got it. Okay, well, that wraps up this lesson. Couple important things before we do our summary here. You might wonder where you're going to need to know that, and actually that turns out to be pretty important stuff. Networking involves a good understanding of hexadecimal, especially in being able to understand hexadecimal addresses. But this really kind of gets into a computer science aspect of this, and that we're going to keep working with those 1's and 0's, especially in binary. We're going to go on and see how we can add and subtract numbers in binary and how binary is used to code data. So we're going to use that a lot more. Just remember, if you want to go from binary to octal or hex, you just use the expanded form. If you want to go backwards, you use the 4 steps that we saw in this lesson. And converting from binary and octal to hex or back again is all about grouping those digits. Groups of 4 1's and 0's for hex and 3 1's and 0's for octal. Okay, that's it. This is a long lesson, but it's a really important one. So make sure to let me know if you're stuck with any of these conversions back and forth. These will be important going forward. We'll see you in the next lesson.